So this is kind of a top-down view, big picture. It's a bigger version of one of the diagrams you saw earlier. Across the top are the application servers, right? Compute servers. Some of them have GPU.
So Andy, in those first group there, it's actually running a WekaIO client.
First group across the top?
Yeah.
Yeah. So the applications are running on dedicated compute servers across the top. And some of them have GPU accelerators, and some of them on the left side have those hollow circles with W's in them. Those are Weka clients. The Weka client is a local file system, POSIX file system. It presents a local file system, but out the back, it sends the I/O over the network.
So Weka server.
So in effect, if you think of what happens over here with like an NFS client, right? It looks like a local file system, but it translates everything into NFS. We're doing the same kind of thing, but we're POSIX compliant. And we can...
And fast.
Yeah, I'll get to that. We're fast. I think we've made the point about being fast, but it doesn't hurt to keep saying it.
Don't minimize it.
So in any case, even when our client is running on the same node where our storage services are running, right, we do the same thing. We present a local file system, POSIX compliance, and we translate all of the local file system requests into what look like network requests because we have a clustered networked storage solution. So even this client here across the storage nodes still has to be cluster connected, right? And it's still a network solution. All right, so anyway, across the top we have applications running on compute servers, some of which reach the storage by means of the Weka client, some of which can still, through our support of legacy protocols, use NFS or SMB. We also
NFS and SMB are external gateways, so you don't develop them.
We don't, excuse me?
So do you use software like Ganesha or stuff, or you develop the
No, so those are the client, that's on the client side. So those are standard clients.
Standard
NFS version 3, SMB.
So you share NFS, it's not scale out NFS, it's a Linux.
We're not doing anything unusual there because the whole point is our cluster can receive those requests. That's just standard legacy.
Standard NFS,
we can't do anything
on Linux.
Right, we can't make it faster than it is. It has its limitations that are inherent in the nature of those protocols.
No, yes, but many HPC environment use Ganesha. Or,
So I think I understand what you're asking. We have our own proprietary NFS implementation that is scalable. So
on the server side.
On the server side.
On the server side, not on the client side.
So for the clients, we're using the standard NFS and SMB clients. Obviously, we have our own implementation as part of the system because we're a large scale-out storage. We need to support both NFS and SMB in the large scale-out way.
So it's not presented in the unified namespace, so you didn't put anything in there.
We don't provide that.
Okay, just to
that we're just supporting it to be compatible.
And it's SMB
because some of our customers already have it.
Which level of SMB support?
Well, so no, NFS v3 SMB support is through Samba, right? So we're using Samba integrated with our code down here.
What level of SMB
SMB
support?
3.
SMB
That's the current,
3.
most recent.
3.2.
3.3.
It's kind of a mix because we're still in the process of completing the integration. So we have some of the feature content of Samba that's complete. Some of it is still a work in progress. So there are elements of 3.1, elements of 3.2, but it isn't fully 3.2 complete yet.
Okay.
Just on that point, though, getting back to you saying you are presenting that from the cluster layer. So I'm not talking about the usual scale-out storage with a gateway node, which needs its own high availability features. I'm actually addressing like a virtual IP for the cluster using NFS or SMB so that if one of the nodes goes down, it retransfers the IO load.
We're not doing, okay, I'm so sorry I even brought this up.
Sorry.
We are a high performance solution because of our Weka client POSIX implementation. These are for the convenience legacy protocol support of environments that also want to continue to have that connectivity
Yeah.
for convenience. We can't make it any faster or better than what's already there.
No.
We do have that capability, but we don't really do anything special for it.
I understand totally. My question's more on the point from a practical standpoint. I've looked at a number of other scale-out systems, and their method of handling that legacy question is they say, well, actually, off to the side, we're going to put a couple of gateway servers, and there'll be
No.
NFS high availability.
We don't do anything
So
off to
you
the
just give
side.
me one IP that I connect
So
to?
I'm going to show you in the next couple of diagrams, so
Cool.
hold that thought.
Right.
Everything that we do is fully integrated, all right, on the server side.
With the notion of scale-out across the board.
Yes.
Perfect.
Okay. All right, let's just keep going here. All right, so if you think back to that picture for just a moment, the application servers, right, will generate their I/O requests through our client. POSIX client request will come in through what we call our kernel module into our front end. All of it's coming through the network card, and then our I/O is handled in user space, not through the kernel. That's one of the reasons we're very fast, very low latency, is we're bypassing or not using the I/O stack that would otherwise be provided by the kernel. That's one of the ways that we're much faster, right? And on the client side, if you were using NFS, we're not doing anything special on the client side, so that's one of the reasons it's going to be much slower, right? Because the kernel implementation for NFS has its own bottlenecks and limitations that we have not changed in any way.
Andy, can you just
Go ahead.
clarify the kernel
Yes, please.
piece there for a second? Because I'll give you an analogy. So think of, say, Fuse, where there's a kernel component, but most of the code runs in user space. Or NetApp have done something similar where they've taken their Plexi software and there's a small kernel component which they're trying to get integrated into the standard Linux kernel as Zoofs or something like that, the zero user space
Yep.
file system. Are you doing something similar in the sense that you've got a kernel module that's basically just picking up the call for the file system and then redirecting it? And if so, does that make it lightweight for the user? Or?
Just that one step, though, only that one step. After that, we're running completely independently of the kernel.
So would you be trying to push that into the standard Linux kernel? And
No,
get
no,
adopted, or-
we're not doing anything open source. We're
Right, okay,
entirely
you're gonna keep that
proprietary.
completely proprietary and separate.
Right,
Okay.
right.
And another special attribute about our kernel component is, and it has been a weak point for a lot of the other solutions that have kernel components, when you're upgrading the storage, we are an enterprise-grade solutions. The clients actually upgrade themselves. So there is non-disruptive upgrades, IOs run, the system upgrades, while the client realizes, hey, I need to upgrade. The client upgrades itself and IOs keep running. And as far as I know, we are the only kernel-based solution that actually provides that functionality.
And because most of it's outside.
Yeah, which is fair enough. I was just curious about how you were doing it. That open source versus proprietary thing was, I guess, where I was headed to understand. I can see from your diagram that you're keeping it as lightweight as possible, but I think you can't avoid having something in the kernel at some point. You have
Well,
to
it's
have
just
something.
that, again, it's the least possible.
The absolute minimal part, yeah. Okay.
So, continuing as we follow this path all the way through, the front end is going to be cluster aware, meaning that the I/O is going to be directed to the network interface. And as we'll see in the next slide, which explores a little bit what happens on the back end, the destination of each I/O is not random. It doesn't just go anywhere. It's going to go somewhere within the cluster based on the best likely destination. It can, if necessary, be redirected within the cluster, but in a very high percentage of cases, it will go to the correct destination. So that's where some of the efficiency is obtained. Right, so the front end, it can be directed to the back end, And as I pointed out, I joined the company in October. Very interesting thing I've recently learned is the horizontal arrow here looks like it's an internal memory path. It actually is a loopback, right? So for the sake of keeping our architecture as clean as possible, everything is really the same I/O path. And so I just told you that there's kind of an awareness or knowledge of the correct destination, and that's true. It knows the correct destination might be on the same node that it's already resident on, in which case it would still use a network address, but it would be a loopback network address.
But that's effectively still just a memory call, or almost indirectly a memory call, even though you might go through the right protocol.
Well, yeah,
you're probably just doing a memory call anyway.
Right, it's going to be an address. It could end up being optimized in terms of the way the binary executes, but
It means if the
it's
data-
going to look like a loopback.
It just keeps it generic enough to allow it not to have to do
So if the
two
data,
choices.
so if the data is on another node, it just follows the same path and it finds it,
It always follows the same
and
path.
you reduce the complexity on the code path.
Yeah, exactly. Yeah. You don't have to write two scenarios for
Yeah.
two different pieces.
Yeah. All right, so the last couple of things I'd like to point out is that the network access is optimized by using SRIOV. This helps us also when we take the same binary, move it into the cloud, or if we run, as we do on occasion, not our preference, it's not the best way to get the optimal performance, but if we're running inside a hypervisor. So regardless of how we're deployed, we're going to be able to get optimal network performance because of this part of our software implementation. And the other thing is, over here, in terms of whenever we access the SSD, our agent is very aware of the hardware in the NVMe device. So we don't just use it generically dependent on the kernel or on the drivers that are provided with the kernel. We have kind of an intimate implementation method. This creates some of the issues, like there was a question about GCP earlier. The guys on the Google Cloud Platform are reluctant to reveal the nature of their hardware at an intimate level. But we are in conversation with them.
So Andy, you might be going to discuss it on the next slide, but in the green boxes at the very top, how are those processes running? Is that the containerized components?
Yeah, everything is implemented with an LXC container design. So now when we look at the storage services themselves, it is a cluster, minimum of 6, could be more, right? And all of it is designed for and written for flash. In fact, it cannot directly address hard disks. There are no data structures that are written for things like cylinder groups or any of the other anachronisms that you'll find inside most other file systems. And one of the things that allows us to be fundamentally different and faster, like the example that was given a little while ago with untarring a large number of small files and so forth, it's usually a bad idea to put hundreds of thousands or millions or billions of files in the same directory. But that would be quite convenient in a number of use cases, in genomics, in machine learning, where you're collecting files that are automatically generated, by perhaps IoT devices or anything that's automatic without human involvement. Maybe just dump them all into the same directory. And before long, you've got a huge number of files. And then it takes somebody's time and decision-making to figure out how to reallocate it. But best practices would tell you that you better do it, because over 100,000 files, usually the file systems start to break. And before that, they even start to slow down pretty noticeably. We don't have those issues because we don't have any of the designs that were written into the older file systems about how to lay out the metadata associated with all the inodes, for mapping where all the blocks are, for all the files on all the hard disks. We don't have any of that, right? Because the nature of NAND for flash is that it's all random access.
Right.
So why should you have any of those anachronisms in your code? Well, one reason is you've got millions of lines of code. If any of the other providers of solutions and storage, you already have it. It ain't broke, don't fix it. So just go in there and optimize for flash. But you're not going to rip out code that works
Yeah, but
Right.
when you build from the ground up for flash, you don't have to even worry about it.
Unless you're an old hand at storage and you've written file systems before, and it's going to influence your thinking. And the team that developed WekaIO, they are old hands at storage. They have a lot of experience, but their experience was not about writing file systems. So when they visited this, they had a clean page in their minds about how they would design a file system. And this fresh view of how to do it did not include, well, how are file systems supposed to be written? So one of the things that's been really refreshing for me as I've been coming to this company and learning what they've done is just how really new many of their ideas are for how the data has been laid out, how the data structures are written, and so on. So just to try to keep things moving along and stay on time. The metadata is striped across all of the devices, meaning all of the servers, as well as all of the storage devices on all of the servers. So everything is fully distributed. This is a case where I'm sure, having been around the industry a long time, one of the goals of any large system as you scale it out is that you want to show that it scales linearly. Right? You want to show that if you double, it doesn't slow down. As you grow and grow and grow, it doesn't slow down, right? This system scales better than linearly. It's super linear. As you give it more resources, it actually gets faster. And that's not really counterintuitive when you stop to realize that giving it more resources means that those more resources can participate in things like making more data paths available in parallel to get to all of the metadata. And as all of us have seen, access to metadata routinely is the bottleneck for almost every application use case. It almost always comes down to metadata. Because if it's a large file I/O sequential problem, well, once you get at the beginning of it and just start reading or writing these large files, that turns out to be one of the easier use cases to solve. And when you have a large number of files, the opposite is true. It's not about just doing sequential I/O. It's about finding the data before you can do anything, or it's about getting permission to have access to the data, and that all boils down to metadata.
I still find that completely ironic. That the whole concept behind metadata was an effort to alleviate that issue. And it actually creates an issue when you go towards multiple small files.
You're absolutely right about that. There is an irony to it. And the irony also goes all the way back to the very beginning when there was a small amount of data and everything fit on like one disk. It was a very different class of problem.
Sure.
Right. And also all of the metadata associated with the data on the disk could be loaded in memory. Right? And what was different back then? It meant that all of the metadata was in memory, which meant that all of it could be accessed directly, randomly, right? With that. So, we're kind of coming full circle here, right? By treating the metadata with as many direct paths as possible, by fully distributing it, we can get much better performance than we've ever seen before. And that's what we're demonstrating with all these benchmarks. That's what we're demonstrating with the use cases that Laurent will be telling you about shortly. We've got one use case he's going to tell you about. I don't want to take up too much time because we don't want to run out of time. We have one where the customer routinely, day in and day out, week after week, sees an 80x speed up over anything else they've tried. And if you don't think that changes their life and their competitiveness in their industry, right, you're really missing something. It makes a big difference to them, and they quietly tell all their friends. So it's been pretty exciting for us. All right, so to get back to this, the data protection, there's been a few references to it, so you already know it's similar to erasure coding. The math looks pretty similar, but it's not Reed-Solomon or any of the other implementations that have been done because the math behind it is a little bit more efficient for us to implement, so it doesn't affect our performance. But it accomplishes the same goal, and it is fully distributed. And accomplishes the same goal. We have optional hot sparing. Now, ordinarily, the idea behind a hot spare is that you want to have devices that are right there ready to take over when another device fails. But a virtual hot spare is a better idea because it means that all of your hardware is in use all the time, so that you can distribute your load across all available hardware instead of just having something idle waiting to be used if something else fails. And that's what we do. We have virtual hot sparing.
Andy, can I ask you
Sure, Chris.
a relatively high level question, but possibly not, depending on. Can we go back to your previous diagram where the one where we sort of stuck on the NFS discussion for a while?
This one?
No, before that.
Oh, the very first one?
Yeah.
Oh, God. Okay.
It's all right. It's actually not a hard question, I don't
This one?
think, but it just might. It's just a conceptual thing I'm trying to get my head around. When you look at the clients that are running with a little W in the green at the top, and they're talking to the storage nodes, does the client software running on the nodes at the very top talk to processes on the storage nodes, or does it talk directly to the devices on the storage nodes?
You mean the device, like the NVMe devices?
When
and
you're
so forth?
talking from the client, are you talking client to client, and then the client in the storage node talks to the actual physical storage?
All right, so the client presents a file system. It generates requests, which are reads, writes, or metadata requests that go out on the wire.
Yeah.
Those are received by these black circles here.
Yeah. So there's
Which are the
target processors which are listening for that.
Yeah, which are listening for that.
And is that across NVMe or an equivalent or something similar? Or
No, those are going
or
to
is that
be,
straight-
now I'm going to go forward to this guy here. So that is going to be basically, give me these arrows. Where are the arrows? All right. So basically, that's going to be from there. Those are the green circles, the hollow green circles out on those remote clients.
Yeah.
I/O coming in over the network, and bidirectional, because sometimes it's a read request has to come back, right? So it's talking to this software here
Yeah.
through this device, which is a network interface card.
So it's a proprietary protocol talking between the network devices.
Yes.
Right.
Between the processors running on the client and the target, effectively.
Yes.
Yeah. Okay. Thank you. That's all I needed to know. I'm just trying to get my head around that a little bit to understand how that was happening.
I'm just going to follow up on that. And low-level stuff, are we talking TCP, UDP, multicast to getting to the cluster?
It's over TCP/IP.
Strictly TCP?
Well, it can also run over UDP, but that's not ideal.
It's always, yeah. It can be for certain workloads, but yeah.
Right.
So our code actually is similar to TCP/IP. We're not leveraging the Linux kernel networking stack because it wasn't designed with performance in mind.
That's where I was at.
And we're leveraging standard TCP/IP networks. You don't need to configure priority flow control or DCB or the other stuff that basically kept FCOE out of bay, and we think may keep the rest of the NVMe of a Fabric ecosystem out of bay. And we also run on Amazon and completely standard Ethernet networks. Obviously, we also run on InfiniBand, which has less issues.
Yeah. All right, the other back-end storage services involve what you've been hearing about for tiering out to the object store. And we use the S3 API to communicate to the object store. And we use that kind of as our equivalent of a SCSI protocol for talking to hard disks. Because as I've already explained, our software doesn't know hard disk, right? So the way we talk to hard disks is through S3. And we can scale this to exabytes because that's what's available. And the name WekaIO actually is 10 to the 30th is Weka. It's a Greek prefix. So that's sort of a little joke. Exabytes or even wekabytes. I don't know if any of the object storage vendors are planning to go that large, but they do talk about exabytes. And that amount of storage is relevant to some of the use cases that we're helping to drive. But no one that we've talked to is planning to put petabytes, let's say 100 petabytes or more, all in flash. But they are talking about putting hundreds of petabytes of data out there, and they want to be able to manage it in tiers. Right? So one tier might be in the object store, and we're very efficient at making sure that when they go to read and write it, it's in flash for them, gives them very good performance.
So that tier is effectively one bucket on an S3 object store? Is that per file system or file share?
Per file system. per file. I was about to say, it's not all one bucket, but per file system.
Per
And you
file
can have, and you can have many file systems, logical file systems. Now, what's different, and this is actually important, I'm glad you asked this question. You can have a storage cluster from WekaIO, and that cluster is distributed across all the available hardware resources. And now you can declare within that cluster many file systems. And each file system is a virtual construct which still shares all of the available hardware. So even if you have a little file system, for some reason you want to segregate it logically, different permissions, whatever, and another one that's very large, the little one still has the same performance because by virtue of the amount of physical hardware that it's distributed across, the same performance as the large
Can
one.
I have the country? Can I throttle a file system back?
You're talking about like quality of service controls?
Yes.
In theory, and it's on the roadmap, but we don't currently offer a mechanism for that. But we could. It's just not a high priority. Currently, everybody just wants everything to be as fast as possible. So it hasn't been a high priority request.
Oh, yes, but if you are adding workloads on top of other workloads,
Well,
sooner or later somebody will ask for it.
I'll tell you who is asking for it. We have a number of service providers that are deploying our software who now are providing separate file systems per client. They would like to do QoS. So it is on our roadmap. It is something we can do and we will. It's just, like I said, hasn't been the highest priority. Currently, we're not really exhausting the capability of the system. So as long as all of those separate customers are getting plenty of performance, nobody's stepping on anyone else, no one's being injured by the fact that someone else is getting great performance, it's still not that high a priority. But eventually it could be. Were you going to ask a question?
Yeah, so the data protection aspect of this. So if I have multiple file systems, is the data protection, if it's spread across all the back-end nodes, then if there's a problem, I guess it's not an issue. I'm just trying to think. So as you're tiering it to one S3 bucket, but the data protection portion of that is different than the data portion or data objects of it. I guess it's okay. I'm still trying to figure out how this
So when you
works.
do a snapshot, the snapshot is for a file system.
Right.
So your snapshot within this file system is separate from a snapshot taken within a different
And as I
file.
tier it, it goes back to its particular bucket.
Yeah, and now if you wanted to rehydrate a snap to object, it
point
would
to the
be
bucket.
for that file system, separate from another one.
Right.
Right, so it's for data management.
Right. But you kind of have this distributed metadata and data protection and data across the physical cluster, but as you tier it, you're effectively isolating it on a file system basis.
Yeah.
Okay.
And if you think about it also, for those users that are on S3 because they're running in Amazon, that makes sense too, because it's not as if we're going to physically partition S3.
And just on the S3 as a protocol generically, so if I'm running some other kind of in-house S3 cluster, we can use that?
Like
Well, quite often-
Yeah, so that's the scale of it, but it's just, is it specific
Do you have the customers
partners?
that...
Okay, so it's for specific partners like Scality that have been, I would say, certified conformant?
Yeah, we don't have an official certification, but we do test before we deploy. And so we're very thoroughly tested with any of the ones you saw listed there,
partner
like
list, yeah.
Scality, Cloudia, and a few others.
Okay.
WDC is the one that's most widely deployed. They're active scale. That's why, no, that's not a picture of active scale. I tried to find a picture of it. That's just a generic bunch of disks
Bunch of
in a rack.
disks,
I suppose that if a customer deploys your software on AWS, then they use S3. Okay, but what happens for a customer that deploy the software on the premises? Are they using Cloudian and Scality, or are they still using S3?
They could use S3, but then there's a latency issue to the cloud depending on their
Yes.
connectivity.
This is the question, in fact.
Or they have to choose what they want to use on-prem. And we are usually part of that dialogue.
Okay.
Right, we're okay with it as long as it's S3 compliant, as many of them are now.
Yeah, but there is also an issue regarding the fact that if you lose the connection, you lose the file system. Access to the file system.
No. Well, it depends on how long it's lost and if everything's okay when it comes back. And that's one of the reasons we do test before we say, yeah, it's okay.
No, yes, but if I have my file system on the premises and I lose the connection to Amazon S3,
Yeah.
even if for an hour, and I just need a block that is on S3,
Yeah.
I can't access that block.
You'd have an error at that
I
point, right?
think
Simone?
what we see, so usually we see customers tiering to on-prem object stores, like Andy mentioned, like WD, Scality, others that we support, and that's their high performance, tiering, expanding their flash capacity, because then you get really good throughput on-prem, and it's less error prone. When they're tiering from an on-prem system to AWS, it's usually in conjunction as a backup.
Okay,
so
yes.
they usually just push snapshots onto the AWS S3.
Disaster recovery.
And
data
then even if
protection.
you lose that connection, everything is still okay.
Yeah, okay, very good.
Great.
Wanted just to be sure.
This is my last slide. I was going to remind you guys about being able to rehydrate and being able to mirror and all that kind of stuff here. I think that got discussed quite a bit earlier in some of the other talks. So I don't know if you have any other questions for me. Otherwise, I can
So
turn
Simon, the question with respect to backing up, you're going to back up a file system to another file system that's tiered to S3, let's say. Can you do a cross-file system snapshot like that? I mean, I just don't understand how it's working.
So you have several ways of doing it. One of them is exactly what you mentioned, to have a file system that can be pinned to flash or tiered to a local object store, and you use several utilities to periodically sync it to a different file system.
Or copy it effectively.
Or copy it or
Yeah.
sync it, and then push that snapshots. I do know that we're talking about also about an upcoming feature that will allow you to do that in parallel.
Oh, okay.
You're basically asking about consistency groups among several file systems.
Yeah, I think that, my question really was, I see how you've segregated the object tier to a file system. I think that all works, but when you start talking about backing up to S3 because the performance is bad or something like that, then you've got to have some mechanism that crosses those file system boundaries to copy that data. I was just trying to understand what you had there. And I understand at this point, it's all standard stuff. It's just not something you specifically support. Okay.
One last question. Chris? NVMe, in terms of support for drives, clearly you're talking to the drives directly. What about the new features that are coming out within the latest protocols of NVMe that are around things like drive partitioning, the faster, the namespaces, all that sort of stuff, faster memory on the drives and things? How quickly will you adopt that and put that into the product?
As quickly as it makes sense. We are in close contact with all of the major NVMe device vendors,
Right.
and we get early access to a lot of their forthcoming hardware. The thing we're focusing on right now, I think it's fair to say, QLC, seems to be the thing that would make the most sense for us to have a sense of urgency about.
Okay.
But where any of the forthcoming features make sense for us to integrate, we certainly have access.
Right. So as Andy said, we are now, when we'll end up announcing later, but we will end up announcing QLC-based features allowing extremely large installations that could be flash only at hard drive-like economics.
Yeah, cost effectively.